Our second speaker continues the theme of looking at new models to ensure that the potential of concrete roads is realised. We've often anecdotally talked about at BrickPave how concrete roads are best for whole life cost, particularly on the budgetary side. Increasingly, though, we're wanting a tool that can show how concrete roads provide the better whole life CO2 solution as well. And with that in mind, we've been working very closely with Michal Drewniok at the University of Leeds, who has developed, together with BrickPave, a model where you can input both asphalt and concrete values and find out which is the best solution. I'm hoping it's concrete.
Good morning, everyone. My name is Michal, and I'm a lecturer in civil engineering at the University of Leeds. Both with Joe, we prepared the presentation. Unfortunately, Joe cannot be here, and I'll be presenting his part, so I think I can handle it. First of all, I would like to mention that my background is concrete. The concrete, for me, is the best material ever. And working at the University of Leeds, where Adam Neville was one of the professors, it's a great privilege to work there, actually. The presentation, we have 20 minutes, 23 minutes presentation, so I try not to extend this time. Before I start, I also wanted to highlight that sometimes during my presentation, you'll find very detailed data. I try not to be very academic focused, but try to hide some statistics behind, because it's very important for all of us to understand what the embodied carbon is. Maybe you know that. I'm pretty sure that you are familiar with that. But I'll make the journey across the whole life carbon, and then I'll present a few things regarding this tool that we are developing. So I will start with the background, then I will show why it is important. I will tell about embodied carbon a little bit, and then a few slides I will just present what this tool can do and what actually the user of this tool has to do to get the results. At the very beginning also I would like to highlight that this tool is not a design tool. Is a very early stage decision-making tool. So all of the data that are going to or can be implemented in this tool are already designed or already assumed by the designer. So it's not a design tool. So let's start with the background. We know that we have a design manual of roads and bridges. We are using those kind of manuals currently, and we know that the guideline shows what the pavement we can use or how we should design them. So the technical requirements, according to those guidelines, we need to have before we even start or when we start the skimming design, we need to have 3 standard designs. We have to compare them, and we have to do the comparison between those different types of pavements, and the design shall be carried out by using the minimum of the 3 options, covering a range of pavements, and they include a flexible with the asphalt base, flexible with a hydraulical bond, granule mixture base, and at least 1 type of rigid pavement. Because we have 3 different pavements that we have to consider, we will need to find which pavement, according to which metrics, might be the best to choose in the end of the day. The English annex for the CD 226 requires to have the whole life cost procedure, and also in some part of the guideline it also requires for design, non-standard design, to compare against the carbon. But we tried to, when we started to think about the tool, we decided to not only to compare those 3 different types of pavements according to cost, but also to include the carbon as well. The CD226 includes the different steps where you have to look at the whole life cost. So the steps are displayed on the slide. So from the develop options, we are looking at the life cycle plan, life cycle cost, and then end up in the option selection through the sensitivity analysis. Regarding the standard designs, I think all of you are familiar with these graphs, included in the design manual of roads and bridges, and they present how we can choose the different thicknesses or different base for different solutions, such as flex composite and fully flexible, and for rigid solution, for continuously reinforced concrete base and continuously reinforced concrete pavement. It doesn't show any, as far as I'm concerned, of course, but I know I might be wrong. It doesn't show any roller compacted concrete, and that solution is not also included in the calculator. However, we can, if it's needed, we can implement it as well. So when we are looking at the guideline, there is a example of whole life costs that is required to choose the right solution for our purpose. And as I mentioned, currently there is only cost included. So there are 3 different options, 3 different costs: discounted costs, residual value, and options, and then promoted options that we are going to and we would like to choose for the design and to build. So based on that, we decided to increase this part, but of course as well as embodied carbon through whole life of the pavement. Previous work by BritPave was done by Dr. Maes, and this calculator, which was, I think, developed a couple of years ago, included only costs, mainly costs, and it was calculated against different, against initial costs, placement costs, and maintenance cost throughout the life cycle of the pavement. But again, because the carbon, embodied carbon, and in general we are going towards net zero carbon by 2050, we decided to include this carbon, the embodied carbon, in the construction in this calculator. So that's why we started to do the work in this area. So building on the previous work, I was asked to redevelop or to develop this calculator to include the whole life carbon as well as whole life cost. And as I said before, it's not a design tool. It's just a decision-making tool according to the design that is already assumed by the designers. And it compares the different solutions according to the whole life cost and whole life carbon. And I will, in a couple of words now, I will just present in a couple of seconds what the embodied carbon is actually included in this tool. Of course, we can't forget about the maintenance regime. So we are under development the maintenance regime for the UK. So the maintenance regime for the different pavement solutions would be also included. The idea of the tool is that everything will be transparent. So we can check all the assumptions. All the transparency would be included in this tool. There is no hidden cells, and all the values that are either cost or carbon would be available by the user. wanted to be very user-friendly, the input should be very, very easy to do by the consultant or by the engineers, by structural engineers, or by the civil engineers, based on the very simple assumptions. That's the first look of the first page of the tool, based on the length, design life, analyzed period, traffics, and so on, so on, so on. Addressing those kind of assumptions, we can then get the final one of the final results. The cost data and the carbon data is going to be verified by the later on, but it will be transparent, so everyone can just look at what data were picked actually for the analysis. And as a result, for example, that's the very example of the results. So at the end, the user can actually take the report. The shape might be like that. On the left-hand side, the assumptions, and then the cost, capital cost and whole life cost, as well as capital carbon or whole life carbon. And on the right-hand side, the distribution of cost and carbon along all across the life of the pavement or different types of pavement that we decide to design. So as you can see here on the right-hand side, you can visually you can see what is the what would be the relationship between cost and carbon along the life. But let's stop a little bit and let's think about why is it important. One thing, why it's important, because we have a design manual for roads and bridges that requires cost. But what about carbon? So just a few statistics that I would like to show you, just to visualize ourselves why we do that, why we, as an academic, in the academia world, why in the UK, why globally we are doing that. So approximately 6% of energy-related carbon emissions are related to non-building construction, which means infrastructure, including roads, bridges, tunnels, and those kind of things. Over the last 30 years, the population increased by 50%. I was born in 1982, and since then the population increased by 75%. And we are going to double the population by 2050. So 8 billion people was, I think, last year in November. So 1 year ago, we reached the 8 billion people population. And also what is very important, that the urban population increases dramatically. So by 2050, we're expecting to increase the urban population by 75%. So we need to deliver, actually, the buildings and the infrastructure to allow the people, us, to live in this world. As I mentioned, because of the increase of the population, we are going to increase dramatically the floor space. So the projection says that we will double floor area of buildings. We will double floor area of buildings by 2050 compared to 2017, mainly in China, Africa, and Middle East. However, I just pointed out on the left-hand side, I recalculated to the 2050, because the 2050 is our actual goal in the UK. We are going to increase the floor area by 25%, by a quarter. So because we need to increase the floor area, we need to deliver the infrastructure, so also roads. Yeah. To visualize it, what we are dealing with. We are dealing with how we can describe doubling the floor space, floor area of buildings by 2060 is just like adding the equivalent of Paris to the planet every single week up to 2060, or adding the floor area of Japan to the planet every single year by 2060. So we don't see it today in the UK. 3 weeks ago, I returned from China, from Chengdu. It's enormous. just enormous construction site there. How fast they are building the buildings and infrastructure is just madness. So we are not seeing this here, but we need to be the leader of lowering the carbon emissions and lowering the cost in the construction that we can then pass to the other countries that don't have this kind of know-how. If we look at the UK, approximately 6% of the global gas emissions are from the construction, and you can see here on this graph, approximately 18% of those emissions out of 6% are from the infrastructure. 65% of those 18% of those 6% are from materials that are used in infrastructure. And in the next slide, I will show you where the material goes in the UK construction based on our analysis, recent analysis. On the left-hand side here, you can see how much material by mass is used in the UK construction, or it was used in the UK construction in 2018. That exclude aggregates that are used, for example, for foundations. But that included the aggregates in concrete and asphalt and other works. So approximately 50 million tons of the materials listed on the left-hand side goes actually to the industry in the UK, to the infrastructure projects in the UK. On the right-hand side, you can see that approximately 5 million tons of global gas emissions are actually in the infrastructure area. So it's quite significant. And we can't forget about one thing, as I mentioned, by 2050, we need to get to the net zero carbon. And for now, we don't have the magical innovations to offset the carbon emissions or greenhouse gas emissions. We need to reduce by using as less as possible with as less carbon-intensive material and make our decision very wisely. Now I would like to talk a little bit about embodied carbon. I think you know about some of the things, I hope, but I think it will be excellent to introduce this kind of topic as well. So before at the very beginning, when I started my presentation, I mentioned about the energy-related carbon dioxide emissions. They are not the same not the same as the global warming potential, which is global gas emissions. So in the UK and in all calculations and in the tool that we are developing, we are looking not at the carbon dioxide emissions, but we are looking at the global gas emissions that includes CO2. The share of carbon dioxide emissions within the global gas emissions is approximately 70%. So we need to bear in mind that not all, so if we are using some units, so CO2 equivalent is actually the global warming potential that includes carbon dioxide emissions. And of course, we can calculate what is the share of different greenhouse gases within those global gas emissions, but it's we use in this tool, we use actually the global gas emissions rather than CO2 because it's more relevant for us because we need to become a net zero carbon, which means net zero global gas emissions by 2050 in the UK. I'm sure that you are familiar with a carbon management in buildings and infrastructure standard that is past 2018, that was revised this year, or last year and this year, it was published this year. So what we are in control with in the buildings and infrastructure, we can control the capital emissions that could be called as embodied carbon, and that is mainly before the use of the buildings or infrastructure. During the use, we are looking at the capital carbon, operational carbon, and user emissions. And after the use, we are in control with capital emissions. This standard doesn't specify whether those emissions are embodied or where the embodied emissions lies. So in the next slide, I wanted just to highlight one thought about the life cycle assessment. So according to, we can calculate the carbon emissions, embodied carbon emissions, as well as operational carbon emissions across the life cycle. So we have standards that allows us to quantify the different emissions across the different stages of the life. And we are using life cycle assessment, and we can, based on this methodology, we can, that's the technique that allows us to assess either cost, carbon, or even social aspect across the life cycle. It's created and it's built in a modular way. So on the left-hand side here, you can see the upfront carbon, which can be also described according to the standard as a capital carbon. But of course, depending on a different definition, different boundaries, it's very important for us as assessors who are doing those kind of calculations to be very specific in definitions, because capital carbon can also relate to the embodied carbon across the life cycle. So in any work that I'm doing, it's very important to define what actually the embodied carbon means to us. So embodied carbon, according to the standards that are listed on the bottom, so we have standards that describe how we can calculate it. And of course, before the change of the past 2018, that now is more recent, we, in one of the documents that we published 2 years ago, I think, in January 2023, we defined a embodied carbon and to split embodied carbon into upfront carbon, which is cradled to practical completion. That includes the cradle to gate, and then transportation of the materials to the construction site, and then the construction and processes in the construction. And of course, embodied carbon are all the emissions related to the materials over the life of the structure, building, infrastructure. So it also includes if we do the maintenance, if we do repairs, if we do a refurbishment, all the emissions related to this also relates to the embodied carbon. And of course, in the end of the life of the building or infrastructure projects, bridges, we need to also consider as an end of the life. Those are the emissions that allows us to deconstruct or demolish the buildings or the projects. Transportation those materials to the recycling or waste processing facilities. The emissions related to waste processing as well as disposal. So all the emissions related to materials in the life cycle of the building or the infrastructure projects might be called or are included in the embodied carbon. And that also might be equivalent of the capital carbon according to the past 2080. So it's as I mentioned earlier, it's very important to actually define what we understand behind the embodied carbon. And the past 2080 also presents one of the very good graph, which is the carbon reduction hierarchy. We know actually that if we don't build, we are not spending the carbon, there is no carbon cost or no capital cost. But of course, we cannot avoid some of the structures with increasing the population. We need to deliver buildings, we need to deliver infrastructure projects. So we cannot afford not to build. Yeah? So, but in this kind of area, the savings could be the highest. But we are looking in our world now today, and in our calculator, we are looking at the switching of the different solutions So switching to the different solutions. So what solutions might be the lowest carbon or lowest cost? And then if we find the lowest cost or lowest carbon solution, how we can decrease the carbon or cost even more. So I think that is a very, very good representation of where the savings can be made, both from the cost and the carbon, and of course, social aspect. So 4 slides about the road pavement, whole life cost and whole life carbon calculator, the bridge pave tool. So we are using a upfront carbon as a main metric, but of course we are including a maintenance, repairs, replacement, and refurbishment. So all the regime that needs to be done, or all the works that need to be done during the lifetime of the pavement, whether it's 40 years, 60 years, 100 years. So we can and we are going to implement this kind of regimes within the tool. Of course, we are including end of the life, but only for the materials that arise from the maintenance, refurbishment, or replacement. We are not including the end of the life of road or pavement. We can do that later on, but for now, I think it's much more important for us to implement what is actually what actually is needed to make a decision today. For the next 50, 60 years. However, it will be very important to include this from the circular economy and lowering the future carbon perspective. This tool doesn't include yet, maybe in the future, doesn't include the construction wastes. We know that we have, the material that is assigned to the tool is only the design material. We are not counting for the material that is wasted, so over-ordering, there is no information about over-ordering. If we have a data for that, we can, in a very quick way, include this, but there is no information about how much concrete or tarmac or asphalt is wasted on construction site. I don't know it. If we know the data, we can implement it very successfully and very quickly. So the tool will include the material cost. It will be transparent. The construction cost as well, so not only material costs, but how much it costs to actually to place the concrete, to place the pavement, to place the asphalt. Embodied carbon. The tool currently lists approximately 90 different asphalt mixes, 40 different concrete mixes, and those data for the embodied carbon, so all the modules from A1 to A5, cradle to gate, cradle to practical completion, use phase, and then the end of the life, are either from the environmental product declarations that are available, publicly available, or available databases such as IC3 or IC2 developed by the University of Bath, or available literature. So that's some kind of mix of the data that we found and that are included. Of course, all the sources are already included and embedded in the tool, so everyone can just look at where the data comes from. And now we are at the stage of specifying the maintenance strategies, and now we are working on that. What should be done over the period of the lifetime of the pavement, according to the different maintenance works. So that shows a slide of what the input data looks like. So for example, for the rigid design, all the green cells are fixed. You can't change anything. But of course, you can change the cells with a blue fonts, and most of the cells have a drop-down list that you can choose the material from the drop-down list. And for example, for rigid design, you can specify the concrete, you can specify the asphalt, you can specify the cross-sectional area of the reinforcement. it's already embedded in the tool. For example, for a flexible composite design, because of the different structure, you can also have a different types of the material that you could use as a designer to compare one solution against another. And decision of the use of the material are already taken into consideration embodied carbon and the cost, so that automatically gives you a final result. For fully flexible design, exactly the same. So the user of the tool has to just go through 3 different, very simple Excel spreadsheet tables, and just to pick the assumption that he or she just made, and according to which the designer designed the pavement. And as I said and previously showed, that is the final product, the final results. So that shows the different, on the left-hand side, the assumptions, the cost, the carbon, both capital carbon or upfront carbon, and whole life carbon, that the solution that we are considering. And on the right-hand side, you can see the cost of the different solutions, as well as whole life carbon for a different solution, including the maintenance regime and including the end of the life of the material that needs to be replaced or removed from the replacement or refurbished. I think that is the end of the presentation, and we are now at the stage of, as I mentioned, of developing the maintenance regimes. If you have any questions, if you have any feedback, please feel free to ask. It will be very important for me as a developer or redeveloper of this tool to get your feedback, because in the end of the day, you are going to be the user of this tool. And if you feel that something should be included or not included, just that's either now or after the presentations. I'll be all day today just to. I'll be asking to give me a feedback. What do you think about it? Thank you so much.
Thank you.